All right. Okay, so today we're going to talk randomization tests and Bootstrap. Okay, so this is another aspect of computational statistics, and so we will take a look at that. Now, before we get into it, we're going to do just spend a little bit of time reviewing topics from introductory statistics, specifically the hypothesis test. Okay. So is anybody willing to give me a definition of what a p-value is? We all take intro stats, right? So, okay. So anyone want to define a p-value? If you're going to call yourself a stats major, and I don't know, not all of you are stats majors, I realize that. But if you are a stats major, this has to be something you gotta do. No volunteers? Oh, we'll try it out.
It's the probability that given the null hypothesis is true, that you get a result that's like as extreme.
Okay, yeah, that's good, right? It's the probability of getting your result or something more extreme if we're assuming given that the null hypothesis is true, right? And so with a hypothesis test, we always start off with the null hypothesis, which is that we generally start off with kind of the status quo, or if we're comparing groups, we might say that, that there's no significant difference between the specified populations, and anything that we observe, any difference we observe is due to sampling error. Sampling error being the fact that when you take random samples, it's random. And so because it's random, you might get a value that's a little bit bigger than what you expected or a little smaller than what you might expect. And the null hypothesis says that everything, all of the differences we're observing in our samples can be explained by just sampling error. Okay, and the p-value is the probability of obtaining a result equal to or more extreme or more unusual than what was actually observed if we assume that the null hypothesis is true. Okay. Now, how did we, so let's say you were doing a t-test. Simple t-test, you've got two samples, okay? And with a t-test, you're comparing the means of those two samples, okay? And when you do that, you end up with a p-value. Where is that p-value coming from in a t-test? Yeah. From the t-table, okay? And what is that t-table based on? The t-distribution, okay. All right, well, where are we getting, where does the t-distribution come from? Or what is kind of like this main idea that says we can use the t-distribution in the first place? Or something that looks like the normal distribution? The central limit theorem, right? So when we are doing a t-test and we're outputting a p-value, that p-value is coming from the t-distribution, which comes from the central limit theorem. The central limit theorem, the main idea of the central limit theorem is that when you take a random sample, the mean of that random sample follows a normal distribution, or it can at least be modeled by a normal distribution. That's the key idea here. And so, you know, those p-values that we produce in your intro stats class, that's based on the idea that the central limit theorem works, right? And that's why in your intro stats class, you probably had to check conditions to make sure that the central limit theorem was valid. And, you know, in your 100A or 100B class, you know, you might prove that the central limit theorem actually works and all of that. So what did I write here? Okay. So that's where we're coming from. Okay. So, you know, in a sample hypothesis test, in a t-test, we would say something like the null hypothesis is that the mean of population 1 and the mean of population 2, those are equal. And if we collect random data, we could get a random sample from population 1, sample 1, and sample 2, we might get that the mean of sample 1 is 10 and the mean of sample 2 is 12. Okay, and we ask, is this difference of 2 points, is that significant? Okay, and the answer, what is the key piece of information that we need to know in order to answer whether this difference of 2 points, is that significant? There are a few key pieces. What are they? So we need to know the amount of variation present within our data, right? If in sample 1, if all of our values are things like 10, 10.1, 9.9, 10.2, 10.0, things like that, where we have very little variation, and all the values in sample 2 are 12, 12.1, 11.9, things like that, then we know that the difference between 12 and 10 is very significant. Okay. On the other hand, if the amount of variation in each sample is huge, let's say we're getting values like 6, 10, 16, so on and so forth in sample 1, and in sample 2 we're getting values like 5, 12, 17, things like that, and we have lots of variation in both samples, then that difference of 10 to 12, that 2-point difference, may not be significant. Okay, so we need to know kind of the amount of variation that's present in each of these samples. Okay, and so yeah, I say the answer is that it depends, and in this case it depends on the standard error, which is a way to measure the variation that we see. Okay. Okay. And so, we get a measure of that standard error, and from that we calculate our p-value, and the definitions of the p-value, okay, is, if we end up getting a small p-value, it means that that observed difference is so large that it is unlikely to see the results that we have if the only source of variation was random chance, right? So if sample 1 has values like 9.9, 10, and 10.1, if those are the typical values, and sample 2 has values like 11.9, 12, and 12.1, and those are the typical values, and every now and then you see, extreme values, technically it might not be impossible to get a difference of 2 points based on random chance alone. However, the p-value will probably reveal that getting that kind of difference is incredibly unlikely to happen. Okay? And so we'll say that in those cases, the p-value is small, so we can be confident that the data we have is not a result of just random sampling, but rather that the alternative hypothesis is true. Okay? And on the other hand, if the p-value is big, that means the observed difference that we got could very well be a result of random sampling. Okay? And we are not ready to eliminate the possibility that the data we have was a result of random chance. And so that's how we make our conclusions. Okay? All of these things, your t-test is what we call a parametric hypothesis test, in that underlying the conclusion of all of that is a distribution that is defined by parameters. Okay? In this case, the mean, the standard deviation, and your degrees of freedom all define the t-distribution that you're looking at. Okay? What we can do, instead of having this t-distribution which relies on the central limit theorem, we can do a randomization test. Okay? And with a randomization test, we are testing the same null hypothesis. The null hypothesis is that there is no difference between the group means. Okay? The key here is that a randomization test does not depend on the central limit theorem, but on the idea of randomization, okay? That's why we call it a randomization test. And the key piece here is the fundamental assumption of exchangeability. All right, and we'll define exchangeability in a moment here, okay? But in short, just so you kind of have an idea, is exchangeability is the idea that one observation can be exchanged with another observation without fundamentally changing kind of the nature of the data. Okay. So this is where we're headed today. We are doing randomization tests. We are not going to rely on the central limit theorem. We're not going to rely on our analytic understanding of hypothesis tests and t-distributions and normal distributions, but we're going to use just rely on this concept of randomization. Okay, so we have to back up a little bit and talk about data collection, okay? Because if I just teach you the randomization test and I don't give you any kind of warnings or anything like that, I feel like it's like, giving you a weapon without giving you any kind of instructions on safety, okay? And so the key thing is how we obtain the data is important as far as when we can conduct randomization tests and the kinds of conclusions that we can make, okay? So here is a silly example, and let's say a dentist wants to know if taking 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C. Okay, so we want to know if people who take vitamin C, if they have fewer canker sores in their mouth. Okay, so we got a few scenarios. This is going to feel a little bit repetitive, but the whole point of this is to kind of emphasize that each of these scenarios are a little bit different, and therefore the conclusions and the applications that we can do are different in each case. All right. So in scenario 1, the dentist, working through the local dental society, convinces all of the dental patients in town with appointments in the first 2 weeks in December to be subjects of a study. Okay, so he's just taking all the people of appointments in December, and then he divides them into 2 groups. Okay, those who normally take 500 milligrams of vitamin C each day, and those who don't. Right, so he says, okay. He asks them, do you take vitamin C, yes or no? Okay, and then he asks them how often they have canker sores in their mouth, checks their dental records, and things like that. He compares the proportion of those who take vitamin C and complain about canker sores with the proportion of those who don't take vitamin C daily and complain of canker sores. And let's say there is a significant difference in the 2 proportions, with a significantly smaller proportion of those taking vitamin C having canker sores. All right. So what kind of study is this? Is this an observational study or an experiment? What do we have? Okay, well, let's talk about this. Okay, well, it's an observational study because he's not forcing anybody to take any vitamin C. He's just saying, do you take vitamin C? Okay, so here, let's see. We selected people by choosing those with appointments in the first 2 weeks in December to be part of our study, okay? So the patients do not represent a random sample from any population, okay? So from our sample, it's not population to make any inference about this result holding for a larger population, okay? So we selected people who had appointments during the first 2 weeks of December. That's not, like, it might feel like that's a random group of people and we don't have anything connecting them, but you know what? They're not random. They're all people who have scheduled dentist appointments, right? Which is not everybody, right? I don't know how many of you have visited the dentist in the last year. I don't know. And so if people don't go to the dentist, they're not going to be caught in this study, okay? So it's not a random sample. We can't make any kind of conclusions about the population. And this was an observational study. We did not tell who's going to take vitamin C and who's not going to take vitamin C. We just said, we asked them, do you take vitamin C or not? And therefore, we cannot make any kind of cause and effect conclusions. So in essence, all we can say is that for these patients, those who take vitamin C have fewer canker sores than those who don't. Okay, so we can only just report exactly the results that we see. We don't know why, and we don't know if this result would be consistent with another group of people. Okay, in scenario 2, okay, we get all the patients with appointments in the first 2 weeks of December to be subjects. We're going to randomly assign half of them to take vitamin C each day, and then we tell the other half not to take vitamin C every day for the next 3 months, okay? And at the end of the study, we study this, and we do see that there's a significant difference in the proportions. Those who take vitamin C have fewer canker sores. Okay, so in this case, again, not a random sample, so we cannot make any conclusions about whether or not this will hold for the larger population. However, the treatments were randomly assigned to the subjects, so assuming other factors were controlled or randomized, the difference in the proportion of having canker sores can be attributed to the vitamin C. Okay, so therefore, the conclusion is, therefore, the conclusion we can make here is we don't know if this result would be consistent with another group, but for the group that we did observe, we believe we know why that the proportions differ. We believe that the vitamin C is responsible for the difference in the canker sores, proportion of canker sores that were observed. Okay, but again, not a random sample, so we can't generalize. Now, you might be able to make some very strong assumptions and say, you know, these group of people are representative of the general population, which is a risky thing to do. But if you're willing to do that, then you can say something like that. But technically, you can't, okay? All right, so continuing here. Now we're talking about selecting a random sample of the dental patients in town and convince them to be part of a study. So we're taking a random sample of people, and then we don't do any kind of random assignment. We just say those who take vitamin C normally and those who don't, okay? We go through. So here, this time, it is random. So since the patients were selected from a random sample, we can infer that the results observed in this study would be consistent with the results from the whole population of dental patients, okay? On the other hand, again, it's an observational study, so we cannot make any kind of cause and effect conclusion. So, so that's what we have, okay? So for the population of dental patients in town, we can be confident. We know that those who take vitamin C have fewer canker sores than those who don't. However, we don't know if it is the vitamin C that causes this reduction or some other confounding variable, okay? And we cannot make conclusions for the general population because the sample was only of those who are dental patients. This is how we obtained our random sample, is that we went through the dental society, who had a list of all dental patients in town, and we got a random sample that way. So this can only be generalized to dental patients, and all we can say is that those who take vitamin C across the population have fewer canker sores than those who don't. But we can't say vitamin C is the reason. Okay, all right, and then you know, if the dental patients in town are representative of dental patients in general, then we can generalize our conclusion. But if they're not, then we can't. Okay. All right. And then lastly, we have random sampling and random assignment, okay? And then, you know, then we do our study. Okay, and then so finally, if you have random sampling and random assignment, then basically all of this says you can make a cause and effect conclusion because of the random assignment. You can say vitamin C is the reason why one group had fewer canker sores than the other group, okay? Because of the random assignment. And then the random sampling then allows you to generalize to the population, okay? To the general population. That's the random sampling. So when you're designing a study, the best case scenario for every researcher would be to have random sampling plus random assignment. But in reality, it's almost impossible to have both. It's almost impossible to get true random sampling and random assignment in both cases. A lot of times you have to pick one. If it's an observational study, a lot of times if you're focusing all of your energies on this sampling part, you're going to get a random sample, but probably they will not all agree to participating in an experiment where you are assigning them treatments, so that you'll probably lose that. On the other hand, if you're doing some kind of medical study, you are very rarely going to do anything with an actual random sample from the population. And instead you'll be dealing with volunteers who signed up to be participants in the study, but you might have random assignments in those cases, okay? But the kinds of conclusions you can draw from each scenario is going to be different, okay? Whether there's random sampling or random assignment involved. Okay, so anyway, that's what we have. So we had kind of the 4 scenarios and the kinds of conclusions you can make here. Okay. All right, is that okay? All of this random sampling, random assignment business here. All right, so let's go back to randomization tests, okay? Exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely, okay? Or that any permutation of the data is exchangeable with any other permutation of the data. All right, so with we're saying, we randomly assign these treatments to some people. So if, on some other day we had the same people, if, we shook up the bag a little bit differently and we assigned the treatments, another way, it's entirely possible to get a completely different set of assignments, okay? And here we're saying that every single one of those are equally likely, and we can exchange one permutation with another permutation, okay? So on a practical level, exchangeability applies only to experiments where random assignment has been used, okay? If we had random assignment in the experiment, then we can say that exchangeability applies to this scenario. So this applies to the scenarios regarding the vitamin C and the dentists, to the situations where the vitamin C treatment was assigned randomly to the participants, okay? Exchangeability does not apply to the scenarios where we just surveyed the people and said, do you take vitamin C or not, okay? Because in those cases, there was no random assignment there, okay? So only to situations with random assignment do we have exchangeability, okay? If the patients are assigned treatments at randomly, any arrangement of patients is equally likely, and in cases where treatments were not randomly assigned, then the permutations of groups are not equally likely. That's the thing. Okay, so I've got a video here that we can watch. It's on, it's from Mythbusters. Mythbusters is no longer on the air, but we'll watch this this thing. Okay, let's see. I hope this works. I might have to put my. Oh, Okay, let's see. We might have to watch a commercial first. Can't hear anything.
A common saying of mine that there's always a better mousetrap. So, as Dello has changed their game, we have changed games.
Okay, sorry, this is a commercial. We'll get it.
And I guarantee you, it's not going to stop there. So how are we going to test whether or not yawning is contagious?
Well, first we need a test audience. We're going to have to isolate them and be able to watch them with hidden cameras.
And we're going to have to be able to control this. Let's say it's a room. We build a room.
Can you guys hear okay?
We're going to have to plant a yawning seed in the room as well.
Somebody who's in on the yawn. That's good. Okay.
I think we can put an ad out on the internet looking for extras, and then we just don't tell them what they're here for. That way we can get them to go sit in a waiting room and we can start messing with their minds.
Yawning is involuntary. The mouth opens and the jaw drops to allow in as much air as possible. As the lungs fill to capacity, stomach muscles contract and the diaphragm is pushed down. The heart beats up to 30% faster. Then, when the lungs are full, excess air is expelled. This time, they are testing one variable only, the seated yawn. Sorry, we're going to sport. Back to your room.
Well, come on in, follow me. In the little room quietly, and I'll come get you briefly.
There's 3 yawn cubicles, each fitted with a hidden camera, and 1 observation chamber, where Tori is on watch. Carrie will yawn at 2 of every 3 subjects as she ushers them into their cubicle.
We're so good on this together. They yawn faster with some influence than without any. Every third person will be in control, which Carrie will give no influence. We'll see if there's actually a difference.
So the experiment begins, and Tori gets down to some careful observation of the subjects doing, well, doing nothing. Absolutely nothing. It's starting to seem like the Mythbusters are just way too much fun to evoke even the slightest yawn. Then, a breakthrough. And after the drought, a flood of yawning is unleashed. The Mythbusters suddenly have the Midas touch. Even the local dogs get caught up in the current of yawns that's sweeping the market. The experiment also suggests that some guinea pigs are more observant than others. And finally proving that all good things must come to an end, 5 hours and 50 test cases later, the Yawnathon draws to a close.
That was it. That's the last one. We're done.
For Carrie, it's not a moment too soon.
I was yawning all day, to the point where my cheeks were hurting and my eyes were watering.
All right. Well, after testing 50 people in the field, our largest sample we've ever used on Mythbusters, the results are in. And when the people we tested got no seed yawn, no stimulus, they yawned 25% of the time. When they got stimulus, they yawned 29% of the time.
Well, it's not dramatic, but it seems like it's pretty good to me. What do you guys think? Busted, plausible, or confirmed?
Given how large our sample was, I'd say it's confirmed.
There's little doubt, it does seem to be contagious.
And I bet the audience at home right now is probably yawning.
All right. Okay, so let's talk about what happened there. What do you guys think? They said 25%, 29%. This was our biggest sample ever. They had 50 participants, and they said 29% is bigger than 25%. Therefore, we've confirmed that yawning is contagious. Agree? Disagree? Okay. Well, let's take a look at this. Okay. All right. So we had they did do random assignment, right? The people came in, and kind of based on the order that they came in, 2 of them got seed yawns, 1 of them did not. Okay, and so because the people that came in, that line could have been in any other order, we can say that this idea of exchangeability holds up, right? Because it's possible just on another day, some people just stood in the line in a slightly different order, and they may, and based on that, 1 person who got a yawn this time may not have gotten a yawn any other time. Okay, so we can say that random assignment was used and the exchangeability holds true. Okay, and then just based on what they've described, they said 2 out of every 3 got a seed yawn, and of those who were given a seed yawn, 29% yawned, and of those who got no seed yawn, 25% yawned. Okay, and so just doing a little bit of math, I concluded that 10 out of 34 versus 4 out of 16. Okay, and they said there's little doubt. It seems to be that yawning is contagious. Okay, that was their conclusion. Okay, so here we can conduct the randomization test. Okay, and what we want to do. Oh, okay, well, first of all, before we go into the randomization test, if you wanted to test if this were true or not, what test would you do from your normal parametric test repertoire? You could do a Z proportion test. That would work, except what are the conditions for the Z proportion test? Yeah, with a Z proportion test, you need to have the large sample condition needs to be met, okay, meaning your sample needs to be big enough. And the general rule of thumb there is you need to have at least 10 yeses and at least 10 nos, right? And in this case, for this one, we only had 16 participants, and we only have 4 yeses. So we technically don't have enough people to do a Z proportion test, okay? But if we did have a larger sample, the Z proportion test, 2 sample Z proportion test would be one way to do it. A chi-squared test would be another way that we could run it. Okay, but this would be a good case to run the randomization test because we have not met the conditions to use a parametric test. Okay, so here all we can do is rely on the use of the exchangeability rule here. Okay, so in the randomization test, we start off with a null hypothesis that yawning is not contagious. Okay, and the null hypothesis would say that the results we saw were just a result of random chance. Okay, meaning that just that 14 out of the 50 people were, quote, destined to yawn anyway, and just because of the way we randomly put some of them into the seed group and some into the no seed group, we happen to end up getting 29 versus 25%. But in another scenario, or on another day, another randomization, maybe we would have gotten something different. So we can test that out. Okay, okay, that's just what I said. So this is what we can do. I'm going to create a vector of this, okay? And we're going to kind of say some are going to be yawning yes or no, and then we're going to assign them to the seed yawn versus the no seed yawn group, okay? Okay, so here this is everybody. This is a vector of 50 true-false values. Okay, and then I'm going to assign the first 34 to the seed yawn group. Okay, and we can see there are, 10 out of 34, and so I can say, what's the mean of seed yawn? Okay, and that says 29% out of those 34 people. Okay, and then for the no seed yawn group, we have 4 out of 16, and the mean of that we have 25%. Okay, and so the observed difference in proportions that we have, if we do this, is 29.4% minus 25%, a difference of 4.4%. This is the data that we have. Okay, our observed difference is about 4%. Okay, and so what the randomization test does is it basically says, okay, what if we mix up these 50 values, okay, of which 14 yawned and the other 36 did not. Okay, we're going to mix up all 50 of those values, and then we're going to just, after we shuffle them, we'll put the first 34 in group 1, and then the last 16 in group 2. And then we're going to recalculate the proportions there. Okay, so that's a randomization test, right? So to do the randomization test, I'm going to just say randomize. We're going to just sample that vector of 50. Okay, and then so here we can see randomized. I just mixed up those 50 true-false values. This is what they are mixed up. And I'm going to put the first 34 into the seed yawn group, or we can just call it group 1. And over here we'll put the last 16 in the no seed yawn group. Okay, so this is with one randomization. Okay, and so when I do that, the mean for the seed yawn group is 26%, and the mean for the no seed yawn group is 31%. Okay, and so the difference that we see here after randomizing is that we get a difference of negative 0.047. Okay, so here those who got the seed yawn in our randomization, if we mixed up the group another way, we actually, in this case, those put in group 1, which is our seed yawn group, yawned less often than those who received no seed yawn. Okay, so this is one randomization. Okay, and we can do this again. We can do another randomization. All right, and every single time we can kind of keep track of the kind of difference that we got between the seed yawn group and the no seed yawn group. Okay, so here, just based on randomization, I happen to get a crazy something, a very large difference. Okay, so seed yawn has all of these trues and falses, whereas no seed yawn only ended up with 1 true. Okay, just from random chance, right? I just randomized the 50 people, and what happened this time was that in the last 16, only 1 happened to, in that last 16, only 1 happened to yawn. Okay, and so in that case, the proportion that yawned in the seed group was 38%, and the proportion that yawned in the no seed group is only 6%. Okay, and so in this case, we're getting a difference of 32%. We got a difference of 32% just from randomization, right? This is not something where we actually yawned in their face or not. Okay, this is just, we randomized, we just mixed up the people, and we put 34 in one group and 16 in another group. And when we did that, we observed a difference of 32%. Okay, and so we just want to know how often do we get differences like ours or something more extreme, okay? This is the observed difference, right? And so we want to know what is the probability that if the null hypothesis were true, that we would get results like this or more extreme. Okay, we want to try to generate our own p-value by doing randomization ourselves. Okay, and that's the big idea behind the randomization test. So we're going to just repeat this over and over and over again. Okay, I'm going to do this 5,000 times, and for each iteration of those 5,000 times, I'm going to just take that initial string of 50 people, 14 of them yawned and 36 do not, and we just randomize them. And then we're going to put the first 30, after we shuffle them up, we put the first 34 in the seed yawn group, the last 16 in the other group, okay? I should just call these group 1 and group 2, okay? Because we're not actually yawning in their face or anything like that. We're just mixing them up. This is the only reason why the groups end up different is because of the mixing up, okay? And then after we do that, we're going to calculate the difference between those who yawn, those who are in group 1 and those who are not in group 2. Okay, those who are in group 1 versus those who are in group 2. And we're going to keep track of all of those differences. All right, so this is the randomization test. Does that make sense what we're doing here with the randomization test? Okay, so we do this, okay? And thankfully, to the power of the computer, it's all done, okay? And it's very quick, and we can kind of see how often our differences work, okay? So the average difference that we observed is 0, okay, or very close to 0, which is kind of what we would expect, right? If we, under the null hypothesis, if the null hypothesis were true, that there's no difference between group 1 and group 2 in the populations, we would expect the difference in the proportions that we observed to be something around 0, and that's confirmed by our mean, okay? Let's take a look. Let's try to get our empirical p-value, okay? So keep in mind, the difference that we observed was a difference of 4%, okay? And so what we want to know is, of the 5,000 randomized differences that we got, how many of them were as large as or greater than the observed difference that we have, okay? So here I'm going to just throw it in here, differences greater than or equal to our observed difference, okay? I shouldn't have done that because I got 5,000 of these. Okay, and we'll just calculate the mean of all of these true-false values, okay? Wait, what just happened? Okay, and it says this happened 50% of the time, over 50% of the time, right? We just randomized this, and over half the time, we got a difference that was greater than or equal to the observed difference that we had, okay? This isn't even, okay, and if I ask for the absolute value of the differences, we'd get an even larger value. Here, this happened, 75% of the time. So with our one-sided test, just with the way things are, this happened about over half the time, okay? Just from random chance. And I could try another, I could say, okay, well, maybe that was just a weird 5,000 sample. So we could try another 5,000. You can do even more, okay? Again, keep in mind, our observed difference, we observed a difference of 4 percentage points. And still, it's something around 50%, okay? Meaning that if Mythbusters ran this episode on another day and they still had 50 people, and we're going to just assume that 14 of them were destined to yawn, they would have gotten a difference of 4 percentage points where at least half of the time, okay? So to me, this tells me that it was very possible, it is very possible to have gotten this difference, observed difference of 4 percentage points just from random chance, okay? So what does this tell us? Basically, the results that we saw on the Mythbusters episode could have been a result of random chance alone. Okay, it doesn't mean that yawning is not contagious. Okay, it just means that the results that Mythbusters obtained, those could have been a result of random chance, whether or not yawning is contagious. Okay, so even in the scenario where yawning is not contagious at all, they could have gotten these results just from random chance, and they would have gotten these results about 50% of the time. So to me, this is not a convincing argument that yawning is contagious. Okay, it could be. It could be. We don't know, right? If we did a study with thousands of people, perhaps we find that there is a significant proportion increase. But our study with just 50 people is not enough to convince me that this is the case. Okay, and so this is the randomization test. Does that kind of make sense? All right, and so the randomization test here, we did one with a categorical variable, whether someone yawned or did not yawn. Okay, but it could be used for a numeric variable. Okay, just like in the way that a t-test checks for a difference between means, here, we could do the same thing. If you use, as long as you use random assignment in the way you've obtained data, you can use a randomization test, because that concept of exchangeability still holds true, and you can mix everybody up. And after you mix everybody up, you then sort them out into two groups at random, or, well, I guess the mixing up part takes care of that. And then you calculate the mean of the first group versus the mean of the second group, and you want to know how often is your observed mean greater or smaller than the randomized means. Okay? And you can do that. Does this make sense? Randomization test? Any questions on this? No. Okay. Then if we're okay, then I'm going to keep moving on, and we'll talk about the Bootstrap. Okay, Bootstrap tests. All right. So bootstrapping comes from the old phrase to pull yourself up by your bootstraps, and there's kind of a theory of how that phrase even came about in the first sense. And there's one theory or one legend is that there's a German folk tale about where the hero was stuck in a swamp, and to get himself out, he pulled himself out by his bootstraps. Okay, and that's something that only folk heroes can do. But this is the name has carried over into statistics. And the idea here is that it's a resampling method. We are going to resample the data that we have to make conclusions about the population without the need for additional data. Okay, and we'll take a look at both parametric and non-parametric bootstrap. Okay, so it's a resampling method in this. Okay. Let's talk about how the bootstrap resampling differs from the randomization test, okay? So, I'll just read this. It says, it's important to distinguish when it is appropriate to use bootstrap resampling versus a randomization test, okay? If the data you have has been obtained via random sampling from the population, then you can use bootstrap, okay? If the data was obtained via an experiment where random assignment was used, then you use the randomization test. Okay, so the first example I talked about was the vitamin C and the doctors, or in the dentist. In some of those we had random samples, and in others we had random assignment, or a combination of both. Okay, when you have random sampling, you can answer questions via Bootstrap. If you have random assignment, then you can do a randomization test. Okay, that's kind of the, in a nutshell, key difference, if I did boil it down to just a simple rule here. Okay. In both cases, we are simulating many instances where the sole source of the variation is random chance. Okay, so that's the idea in both of these cases, randomization test and Bootstrap. But we use Bootstrap when we have a random sample. We use the randomization test when we have random assignment. Okay, so here I'm using an example from the Ziefler textbook, which I have linked. It's in your syllabus, but I've also linked it on CCLE. Okay, so as long as you're connected to the UCLA network, you should be able to access this this book for free. Okay. Okay, so what we're looking at is, it says the Center for Immigration Studies at the U.S. Census Bureau has reported that despite shifts in the ethnic makeup of the immigrant population, Latin America and Mexico specifically remains the country's greatest source of immigrants. And although the average immigrant is approximately 40 years old, large numbers of children who enroll in U.S. school, large numbers are children who enroll in U.S. schools upon arrival. Their subsequent educational achievement affects not only their economic prospects, but also those of their families, communities, and the nation as a whole. Stamps and Bohan, these are authors, studied the educational achievement of Latino immigrants by examining a random sample of the year 2000 census data, okay? And so we've taken a subset of that and put it in the CSV file, latinoed.csv. Did I? Okay, let me upload that. And one interesting research question that has emerged from the research is whether there's a link between where the immigrants originated and their subsequent educational achievement. Specifically, the question is if there is a difference in the educational achievement of immigrants from Mexico and those of immigrants from other Latin American countries. Okay, so whatever we observe, keep in mind this is an observational study, okay? There's no random assignment being used. It's just a random sample taken from the census, right? So the census is everybody. We're subsetting that to just those who are considered to be immigrants from Latin America. And of those, we're going to kind of divide them into two groups, those who came from Mexico, those who came from other Latin American countries. And then we're going to look at the educational achievement of those people. Okay, so let me upload this CSV file, because just if you want to follow along, you will need it. Okay, so that's the data set that we're looking at, okay? And we're losing some of this information, but let me, here, I'll load it and we'll take a look at the data. Okay, so let me clear this out. Let's load up this. We have 6 variables, okay? And so let me just do names. Okay, we've got ID, achieve, year, age, English, and MEX. Okay, so these are the headings, and so we start off with an ID number. Okay, achievement is a measure of educational achievement level. This is a scale of educational achievement ranging from 1 to 100, in which higher values indicate higher levels of educational achievement. I don't know how they assigned these numbers, okay? I really don't know what, I don't know what 100 means and what a 90 means, or what a 70 or a 50 or whatever, right? So we don't have, they did not provide what the exact details of these things. So if somebody graduated high school, I have no idea what number that is, or if somebody obtains their PhD, I don't know what that number is going to translate to, okay? Immigration year is year in which the immigrant arrived in the U.S. Okay, this indicates year to the nearest tenth. So so 81.5 is halfway through the year 1981. Okay, the age value is the immigrant's age at the time of immigration. English is the individual fluent in English, yes or no? And Mexico is, did the individual immigrate from Mexico, yes or no? Okay, and those have been coded into ones and zeros. Okay, so if we just take a look at head of our data set, this is what we see. Okay. Okay, so let's just do some exploratory analysis, and we'll use dplyr here. Okay. So here, let's just kind of see, let's see, is there a difference in achievement levels for those who are from Mexico versus those who are not, okay? And so this can be done in dplyr with just one line. We just take our dataset Latino, we group them by the column Mexico, and then we're going to summarize, and we're going to get the mean and the standard deviation of the achievement column. Okay, so when we do that, this is what we get. Okay, so those who are from Mexico, their mean number is 58.6, and those who are not, their mean number is 64.5. Okay, standard deviations around 13 and 15.6. And so the question is there a significant difference between these two values? That's what we want to know, right? Okay, we can do just create some graphics to kind of get an idea of what this might look like. Okay, let me, I'm going to just click this over here. All right, so this is kind of what the thing looks like. So we have anywhere from the lowest value seems to be a little over 20, and the highest seems to be a little under 100. Okay, this is 1 would be those from Mexico. 0 is those who are not from Mexico, okay? And this is kind of the difference that we see. So we see a lot more spread for category 1 versus category 0. But, is there a difference in kind of the means? Well, the medians seem to be a little bit different, and, the Q3s seem to line up quite closely, but Q1 seems different, okay? And it's hard to really say just from based on looking at the box plot, but this is kind of what we have right now, right? We can also look at density plots, right? So what am I doing here? So I'm going to do create a density plot, okay? And what I'm mapping is I'm going to map the achievement, okay? And we're going to look at the color. The color is going to be mapped to whether they are from Mexico or not, okay? And then the color and fill. So the fill is the color that it gets shaded in, and the color is the color of the line, okay? Alpha 0.2 makes it a little bit translucent. So this is, let's put this right here. Okay, so so the green is from Mexico, and the red is those who are not from Mexico. And is there a difference between the educational achievement levels between these two groups? This is kind of what we're looking at, okay? And so this is, I guess, what we want to observe and try to answer using our Bootstrap tests, okay? So a traditional test is we can just compare the means from using a t-test, okay? And so with a t-test in R, the command you would run is t.test, and we're going to say achieve as explained by the column Mexico, and the data comes from our Latino data set here, okay? And so when we do this, this gives us the Welch 2-sample t-test, okay? It gives me A test statistic of 2.2. Degrees of freedom is this. Okay. Our p-value is around 3%. Okay. This is a two-sided test. We can tell because it says the alternative hypothesis is that the difference in means is not equal to 0. Our 95% confidence interval is this, which is entirely positive. And so this means, you know, based on our data, we would come to the conclusion that the difference in means is unlikely to be a result of random chance only, and that there might be something to you know, we don't know exactly what it is, but it does seem, at least from an observational standpoint, that the education achievement of those from Mexico is a little bit lower from other immigrants from Latin America from countries other than Mexico. Okay, whatever reason that is. This is just what appears to be the case with our t-test. Okay, that's what we have here. Okay, so we've done this. Okay. The question says, what assumptions are we making? What are the assumptions that we are making? Okay, yeah, one, that's a random sample. That seems to be fair because they said they took a random sample from the census data, which is going to be as close as we can get to the population, most likely. So that part seems to be fair. The other part is that the sampling distribution can be explained with a normal model, right? So, which we say is most likely to be true if our what did I say? If our data sets are large, okay, and we can, you know, that might be debatable, but that's what we have. Okay, let's talk about some parametric bootstraps. You know, the t-test might be a reasonable thing to do in this case. Okay. With parametric bootstrap, we're going to make assumptions about the population, and then we simulate many random samples from the said population using R's ability to draw random values from a specified distribution. And then we compare the results from our simulated random samples to the observed results that we have. Let me pull up the code for, where did it go? Okay, so with the parametric bootstrap is we're going to we make assumptions about the populations. In this case, probably that the population looks like a normal distribution. Okay, and then we're going to draw random samples, random values from that distribution, and compare the results I have to the compare the simulated results to the results that we have. Okay, so to do this with parametric bootstrap, what we're going to do is we're going to take the values that we have, and we will we'll scale everything. Okay, so we're going to turn everything into z-scores. Okay, and so we're just going to create a column called z achieve. Okay, so we're going to take the achievement scores and we're going to add a column. And all this does is it just makes everything in this achievement column to have a mean of 0 and a standard deviation of 1, right? So we can kind of see how this affects it. Okay, so it takes all of these achievement values and turns them into z-scores, and we can see that the mean is 0 and the standard deviation is 1. Okay, after we scale everything. Okay, and then so when we do this, we get a mean of 0.3 for the from those not from Mexico, and a mean of negative 0.08 for those from Mexico, and these are kind of their standard deviations. Okay, so what we're going to do here is we are going to generate a bunch of values from using R's random normal function. Okay, here we're throwing it inside a function, but effectively I could just do R norm, 10 with mean equal to 0 and standard deviation equal to 1, and this will generate 10 random values from the from a normal distribution. Okay, and this function, basically all we're doing is by doing this generating function, it's just going to take the length of the data. So in this case, it's going to do 150 of them. Okay. Then we're going to give it a function to calculate the differences, right? And so if we look at our Latino data set, right? And if I summarize this, and I just said how many are from Mexico versus how many are not. So let me just kind of in the summarize. If we just say n is equal to n, we see there are 34 out of the 150. 34 are not from Mexico and 116 are. Okay, and so we're going to create a function to calculate the mean difference of our data. Okay, given a set of indices. Indices here is kind of our randomized thing here. Okay, that we need this when we use the Bootstrap function. Okay, and so basically, if I take my current data set, which is going to be Latino, and I take 1 through 34, I want okay, these are kind of the first 34 values, and then we'll throw the last 116. So the idea here is with the Bootstrap thing, okay, we're going to just feed it a vector, which is our achievement and z-scores. Okay, the statistic that it's going to calculate is mean difference. Okay, so what Bootstrap does is it generates a bunch of indices, okay, and a randomized vector of indices, okay, which is then used to kind of instead of actually shuffling the data, it gives me back because shuffling the data is a little bit more computational work. Okay, what it does is it shuffles the indices 1 through 150, and basically says, okay, once you've mixed up your indices, then pretend you've pasted those indices to the rows here, and now pretend these are, rows 1 through 150 in this order. Okay, rather than actually shuffling the rows, it's shuffling the indices. Is what it's doing. Okay, and so here we're going to say we're going to give it the achievement scores. What we're going to do is we're going to calculate the mean difference, which is just take the calculate the mean of the first 34 and calculate the mean of the last 116. And then the way we generate our random thing is by we're going to compare it to the parametric thing. Okay, so we load up library boot, we run this, and it's done. Okay, that's the Bootstrap. We can kind of see the output that it produces is kind of crazy. If we plot this, we can see this does seem to obey the central limit theorem in that the differences we get look a lot like the normal distribution. Okay. Okay, so, you know, we expect something around 0 if the null hypothesis were true. What we the difference that we observed in our data set was a difference of 0.39. Okay, when we went all the way back and we did this, we got a difference of 0.39. Okay, the difference between group 1 and group 2. So we want to know how often did we get a difference greater than 0.39. Okay, we got 225 out of effectively 5,000 repetitions. Okay, so this happened about 4.5% of the time. So, you know, I could draw kind of an AB line at 0.39. Okay, and this is where we are. Our observed difference was out here at 0.39. Okay, and we can kind of see, you know, how often does that happen? Or I guess at, you know, negative 0.39 also. Can we do negative 0.39 also? Okay. Yeah, so how often do we have an absolute value greater than 0.39 or less than negative 0.39? Okay, when we said, okay, how often is our absolute value greater than or equal to 0.39? It said this happened about 225 times out of our 5,000 repetitions. Okay, and so our observed p-value is around 4.5%. Okay, it's a little bit higher than what our t-test said of about, I forget what our t-test said. What, 2.9% or something around there? Okay. Okay. Here we could do some manual generation of values here. Okay. In case we wanted to do manual parametric bootstrap. With manual parametric bootstrap is we would randomly generate 150 values from the normal distribution. Okay. And then what I would then do is I would calculate the difference between the first 34 versus the last 116. Okay. So effectively, so the idea here in the manual way is we are assigning, we generate 150 values at random from the normal distribution. We assign the first 34 to group 1, the last 116 to group 2, okay? And that's kind of the idea, simulates the idea that all 150 observations that we have in our data set, you know, come from the same population. And we would do that 5,000 times, okay? So here I'm doing the differences, and then again, I could just calculate how often were our differences greater than or equal to 0.39, and I should do absolute value of the difference. Okay, and that happens about, you know, 4%, 3.98% of the time. Yes.
Where did you get 0.39 again?
So 0.39, this is coming from when I summarized my data. So after I turned everything into z-scores, okay, so I took my achievement column and I turned everything into z-scores, I then summarized it and I said, what's the average z-score for achievement for the non-Mexico group? What's the average z-score for the achievement column in the Mexico group, okay? And that difference is 0.30 minus 0.088, okay? So this difference here is basically 0.39. I guess it's 0.388, a difference of about 0.3885, if we're asking. So this is the observed difference between z-scores, the z-score of group 1 versus the z-scores of group 2 in our data set. And this is what we're getting when we do our parametric bootstrap. So with parametric bootstrap, you're making fairly large, major assumptions about the population. In this case, we're assuming that educational achievement follows a normal distribution, which may be a reasonable conclusion because when we produced our plots back here, it might be reasonable to say that the population that comes from this could be a normal distribution. Okay. Now, if you think that the population has a different shape, then you would do that. Okay. You would say the population has this shape, and therefore I'm going to generate my data according to that population. And then you try to say, okay, if I'm generating my data according to the normal distribution, how often does my randomly generated data, how often is that larger than the observed data that I have? Okay, so you're trying to create a p-value through computer simulation. We'll skip that, plot 7.9. Okay, now we want to do non-parametric bootstrap. Okay, this the boot library is actually probably more designed for non-parametric bootstrap. So with non-parametric bootstrap, the idea here is we are not using the normal distribution to generate random values anymore. Okay, we're going to just take our 150 values that we have and then kind of sample from them with replacement. Okay, so a randomization test would have taken those 150 values and then shuffled them and then said 34 go into this and 116 go over here. Okay, with non-parametric bootstrap, you take your 150 values and you sample from that 150 values with replacement. Okay, the first 34 get put into group 1, the last 116 get put into group 2. But because you are sampling with replacement, you will very likely draw some of the values multiple times, and some values will never get drawn at all. Okay, so it's kind of like taking a deck of cards, you shuffle it, you deal one out, you put it back in, shuffle it, deal one out, put it back in, and you're going to deal out 52 cards this way, right? And if you do it that way, you know, you are probably going to get some of the cards more than once, and some cards will not be selected at all. Okay, it's very, very, very unlikely when you sample with replacement to end up getting a full deck of 52 cards that way, right? So sampling with replacement is kind of the key thing with non-parametric bootstrap. Okay, let me see. All right, so with non-parametric bootstrap, we're not making any assumptions on the distribution of the population. So with parametric bootstrap, we are making assumptions. In this case, we're saying our populations follow the normal distribution, or in another situation, we might say, you know, it follows this other distribution, a Poisson distribution, or something like that. Non-parametric bootstrap, no distributional assumptions are made about the population. And the key here for non-parametric bootstrap is that our sample has been drawn randomly from the population, okay? And therefore, it can be expected to be somewhat representative of the population. That's the big assumption for non-parametric bootstrap. And what we do is we draw samples with replacement from the data that we have. We repeat this, and we make comparisons using the resampled data that we have. Okay? So the way non-parametric bootstrap works on R is we use library boot, okay? And we feed it the data that we have. In this case, we're saying data is Latino, and then the statistic is calculated using the function that we do, okay? The function that we give it is a function of our data and the indices, okay? Indices is something that will be generated by library boot, okay? So again, when we do boot and we get, let me see if I can do structure of non-par.boot. I'm not sure where it is. Okay, but basically it's going to just take a sample. What it's effectively doing is saying sample values 1 through 150. We want 150 of them, and we have replace equals true. Okay, and so this is effectively what it's doing. It's going to return back, 150 values sampled from 1 through 150, and it's going to select these rows. Okay, and based on these rows, it's going to put the first 34 of these values, which is pretty much, these ones, into group 1, and then these rows get selected and put into group 2. So, kind of, if I were to do this manually, so here I have, let me just I'm going to store this as indices. Okay, so this is what indices looks like after this time. The first 34 will be simulate those not from Mexico, and then the last 116 will be those from Mexico, and then we're going to just subset our achievement, right? So we do Latino $achievement, and then we're going to subset this on indices 1 through 34. Okay, so these are the these are the values from the achievement column that correspond to 107, 36. So if I, take the achievement column and I say, I just want the 107th value and the 36th value, it pulls back kind of what we have, okay? And so we're pulling these values. So these are the random values that get assigned, and we calculate the mean of this. And then we do the same thing with the other indices, 35 through 150, okay? And this is the mean of, 34 that were randomly selected, and then the mean of 116 that were randomly selected with replacement from the population, or not the population, from our sample, okay? We are resampling our sample using this. And so we define this by saying D is going to be the data that we have, as indicated by these indices. And then we're going to say we just want the achievement, first 34 achievement values subtracting off the last 116 achievement values. Okay, and then so when we do this, this is what we get for non-parametric bootstrap. Okay, and we can kind of take a look at what we get in this. Okay, it looks a lot like the normal distribution again. The mean when we do our non-parametric bootstrap is close to 0. The standard deviation is 3, and that's fine. Okay, and now we want to know how often did our bootstrap resamples, how often did those produce a difference as large as the difference that we observed. So, you know, going all the way back, if we take our data Latino and we group by the column next and summarize mean equals to mean of achieve. Okay, so what we get is, you know, 64.51 minus 58.59. Okay, we're getting a difference of 5.92 between the two groups, and we want to know how often did our bootstrap differences end up being bigger than that difference of 5.92. Okay, and so the value that we are going for is stored in our results under the $T. Okay, so we say nonpar.boot $T. These are the 5,000 differences that the non-parametric bootstrap obtained. So again, the mean and the standard deviation is that. And so we got 256 out of our 5,000 repetitions. So we do 256 divided by 5,000. And this happens about 5% of the time. Okay. And so this is non-parametric bootstrap. Yeah, this is, yeah, that's fine. Okay. And again, the idea with non-parametric bootstrap is that we are sampling with replacement from the very data that we have to kind of simulate the idea of drawing another random sample from our population, which is it feels a little bit strange, but it works. Okay, mathematically it's shown to work. Let me think of another way to explain this. Okay, so another way to say what non-parametric bootstrap does is it says, okay, we're going to treat our sample of 150 people as being representative of the population. That's kind of the big assumption that we make in non-parametric bootstrap. We're going to say the sample that we have is representative of the population. Okay? Therefore, we're going to create our own simulated population. And in order to do that, we just we create, an infinite number of copies of our sample. Let's just say I make 1,000 copies of my sample of 150. So now I have a population of 150,000 people, but really it's just they're like 1,000 clones of these 150 people that I have. So now I have a population of 150,000, and then I'm going to just draw a random sample of 150 from that, quote, simulated population. If I do that, then that's effectively what non-parametric bootstrap is. Sampling with replacement is effectively making an infinite number of copies of your current sample, and then you're sampling from that thing. Okay, so we're trying to say, how often does random sampling produce data that looks like ours or is something more extreme? That's the question that we're going for, right? We're trying to get p-values and all of these things, and we have a few ways of doing that. One is via sampling from a parametric distribution. That's the parametric bootstrap. We're saying using the summary statistics from my sample, the mean and the standard deviation, or I'm going to make assumptions about the population, that it's a normal distribution, and we scale all of our data. We create, we simulate the population using the known normal distribution. That's one way to do it. Non-parametric says, I'm not going to make any assumptions about the population except for this one key assumption, which is that the sample that I have, which was obtained via random sampling, is representative of the population. So I'm just going to take my data and just make 150, or make millions of duplicates of this, and that's going to produce my population. Okay, and that's what sampling with replacement effectively does. Does that make sense? Okay, so you have parametric bootstrap and non-parametric bootstrap, and these are ways to, get p-values and answer questions that we might have without using an analytic method, without using the central limit theorem, which is key for the t-test, or also key for z proportion tests, which is what we've done. All right. Are there any questions? Okay, yeah, again, I would encourage you guys to do the reading from this Comparing Groups textbook on randomization and Bootstrap. And with that, we'll end just a couple minutes early today. And you can expect to see homework 5 posted. Homework 5 is going to be a big simulation assignment for you guys to work through. Okay? All right, have a great weekend, you guys, and we'll see you guys on Tuesday.